Hello, my name is Benjamin Chesser, and I'm in Math 423, and this is video demonstration 2. So, asked me to pick one section from Group A and Group B. So for Group A, I picked number 1, and it says, prove that if K is a subgroup of G and N is a normal subgroup of G, then K over K and N is isomorphic to Kn over N. So, just going to define our terms. So it says K is a subgroup of G. That means that all elements in K are in G and K is closed under the operation of G. Also says that N is a normal subgroup of G, meaning that Gn equals Ng for all G in G. It is possible that the elements that we are using in N are the same, but they need not be. So an element of G, element of N equals element of N, element of G, and elements of N don't need to be the same. Next, it says K over K and N. That can be expressed by writing out the elements of K, and every time a factor of K and N pops up, we write K and N. And Kn over N is expressed by writing the elements Kn, and when factors of N pop up, we just write N. So the steps to show that K over K and N is isomorphic to Kn over N are the following. 1, we define the mapping from K over K and N to Kn over N and verify that it is well defined. We also need to find the kernel. We need to find phi of G, and we want to show that what we found the kernel of is homomorphic. Now that's all I can do for Group A, so I'm going to move on to Group B. That's just the process of solving Group A. I'm just moving on to Group B. So for Group B, I chose number 2, and that says show that nilpotent elements of a commutative ring form a subring. So to verify that the set of nilpotent elements N, I'm going to call that group N, forms a subring of R, we can do the following 3 steps. Show that N is non-empty, N is a subgroup of the abelian group of R, and N is closed under ring multiplication. So we can do that by first showing that it's non-empty. We observe that 0 to the first power equals 0, and 0 is an element of N, thus N is non-empty. Easy enough. Secondly, to show that N is a subgroup of the abelian group of R, we let A, B be elements of N. There exists non-zero integers M and N such that A to the N equals B to the M equals 0. So AB raised to the Mn equals AMn times BMn. So we could break that down by saying A to the N raised to the M times B to the M raised to the N. We know that A to the N and B to the M are equal to 0, so we can set the whole thing equal to 0 and conclude that AB is an element of N. So we do the same for A minus B. We're just for different operations. So now for A minus B raised to the M plus N. We can set that equal to this sum. We know once we work it out that this sum comes to 0, and therefore A minus B is an element of N. So and lastly, to show that N is closed under ring multiplication, we set AB over M. We can break AB over AB raised to the M power. We could set that equal to A to the M times B to the M. We know that B to the M is equal to 0, so A to the M times 0 equals 0. We said that we can write 0 equal to A to the N, B to the N, since we know that A to the N is equal to 0. And we can write AB raised to the N at the end. So A to the B, or AB raised to the M equals AB raised to the N, and thus AB is an element of N again. So since N is closed under both ring operations, we conclude that it is a subgroup of the ring R. So that is video demonstration number 2 for Math 423. I'm Benjamin. Thanks for watching.